Thank you very much for the introduction and being here. So I'm going to start my talk by a motivating application in computer science. So the question is, I'm going to write it down. So find a finite set of rotations. I denote it as set S inside rotation. I'm going to look at them as element inside SU2 such that, so I'm going to identify SU2 with S3, three-dimensional sphere, such that given a cap, C x epsilon, a cap simply means a center, the intersection of a ball with the surface of the sphere. So it's a cap given, a cap is given by a center and its radius, a size epsilon. Inside S3, you want to have two properties. So the first one, there is an algorithm to find a short path, a short word in polynomial in time of the size of the bits that you need to encode this data, which is 1 over log of 1 over epsilon. So in other words, you want to set off a rotation such that I can move this piece of paper by some finite moves to anywhere I want with an epsilon precision. So the second property is I have to quantify this short. So I want the length of the word. So if my word is SI1 to SIH, which is inside the cap, so I want H to be linearly independent to 1 over log of 1 over epsilon. And the main point of this talk is that, in fact, such a generating set of rotation exists. And I'm just going to give you that set, an explicit set. I'm going to denote it by S5. So they're indexed by prime. So for 5, it's just a set of 6 explicit rotations, 1 plus 2i, 0, 0, 1 minus 2i, plus minus 1. So it's a symmetric set. You can think of it as a, we're taking random walk with these explicit rotation on S3. Plus minus 1. So S5 satisfies property 1 and 2. So I'm going to talk about the properties of S5 with property 1. So I'm going to cite some references with regard to log.
Yes, not 1 over log. Not 1 over log.
Oh, yeah. Double, okay, yeah. Thank you. Okay.
Can I ask what the second, clarify what the second statement is?
The second statement, the length of the word should be linear in
Oh, you mean the
log
word that
of.
you find in part 1?
Yes.
Okay, so the word you find that moves, say, the origin or something close to the origin, into this cap, you have to find it in polylog time, and it has to be length linear and long.
Linear, that's correct. It might be the case where the shortest word might be different from the word that
you don't insist on finding the shortest. Right?
Yeah, but that's a question which I'm going to address here. So in fact, Ross and Selinger in 2014 develop an algorithm that returns the shortest word. For diagonal matrices. So if I can only allow myself to move this on rotation with the x-axis, I can find the shortest word. But in poly 1 log of 1 over epsilon. But they have some heuristic assumption. But the main point is that this has been implemented and it works fast. So under some heuristic and a polynomial time algorithm for factoring integers. So once you can approximate optimally the diagonal matrices, you can use them to write every other matrix by simply using 3 diagonal matrices and some generators Si in between. So you can write every matrix G in a short word by using this algorithm. So my first result was to develop the analog of this algorithm for another task. So this is my theorem. So algorithm for navigating LPS Ramanujan graphs. So I'm not going to give the explicit definition of them, but I'm just going to list the property of this graph. So this graph has, let's say, you can make a graph with size 10 to the 100, where the degree of the graph is 6. And the size for every vertices, x and y, inside the graph, the algorithm outputs a path from x to y such that the size of the path is less than 450. So you can imagine it's a huge network, but every 2 points are connected computationally fast by only using 450 edges. So there is a question about what about finding the shortest word by algorithmically, by the algorithm, by an algorithm. So in fact, based on the work of Sarnak and Arzhanchevsky, in 2017, and the work of myself. So finding the shortest path, shortest word for a generic point is NP complete. So you can always find the shortest word. So finding this problem is complete.
And you can give yourself factoring.
Yeah, even under factoring. Okay, so this are the reasons. So NP complete, there is a class of algorithmic problems which are an equivalence class, and solving one of them would be equivalent to solving a problem, solving all problems in the NP complete class. So one of the well-known of them is the sub-sum problem, which I'm not going to state, but solving this problem is the same as solving sub-sum problem. So I'm going to talk about the bounds on the length of h in terms of a linear function in log of 1 over epsilon. So for that, I'm going to define a notion, the notion of a covering exponent for the integral points on the sphere or any quadrics, and tell you how that is related to this word length h. So this is the second part, covering exponent of integral points on quadrics. So the problem that I wrote is equivalent, the algorithmic problem is equivalent to this problem. So we want to represent 5 to the h with sum of 4 squares such that this x1 to x4, if I project it down on the unit sphere, it lies on the cap cx epsilon. So this, if I denote it by x, if I project it down on the unit sphere, so x over square root of 5 to the h. If I can such an integral point, then there exists a word from, then I can find a word of length h inside this cap. So what is the covering exponent? I'm going to denote it by k, is the lim sup of epsilon goes to 0, log of the number of representation of n sub epsilon. So n sub epsilon is the least integer, such that if you look at the integral points which represent n epsilon, and if you projected them on the unit sphere, it covers all the caps of size epsilon. This divided by log of 1 over the volume of ball of size b epsilon. So as it defined by pigeonhole principle, you can easily see that this is always bigger than 1. And there is the analog of this exponent for the average version of this definition, which you don't care to cover all the caps, but you allow yourself up to a delta fraction of the caps. So you have a limit, delta goes to 0, lim sup of epsilon goes to 0, same ratio, log of r n epsilon delta. Now this is the same in the least integer such that it covers all the caps up to delta fraction of them, divided by a log of 1 over volume of b epsilon. Again, the trivial lower bound is k bar is bigger than 1. So what's the relation of them with the h that I said here? So let me first write down the result of Sarnak on bounding h, k, and k bar. So in his letter in 2015, Sarnak proved that k bar is in fact equal to 1. And k is bigger than 4 over 3, and it's less than 2. And he conjectured that k is in fact equal to 4 over 3. And this is by assuming a twisted version, Selberg and Rankin, Selberg and Linnik conjecture. This is known by the result of Browning Kuma, Ras, Wame, and Raphael in 2017. So these are the known bounds on K bar and K. So I want to tell you how Sarnak proved these results. So there is a set of dual points to the integral points on the sphere, which are the eigenvalues of some Hecke operators. So I'm going to talk about the dual picture, the dual points to these integral points, which are the eigenvalues. So eigenvalues. So again, we look at the space of L2 functions on the sphere. SU2 act on this space, and it decomposes into some irreducible representation with some multiplicities. And associated to these integral points on 5 to the h, I'm going to introduce a set of dual points. So for that, we first look at a self-adjoint operator, T5, which is the transition step that we are making. So it's basically the sum of elements in the generating set that I introduced first. So we view this. This is going to be a symmetric matrix on each irreducible representation. So I'm going to look at the spectrum of sim k of T5. It's a symmetric matrix. The set of eigenvalues are real numbers. And since I'm summing 6 unitary matrices, so this is going to be inside interval -6 and 6. But the main point about T5 is that, in fact, this lies in a much shorter interval. It lies inside 2 minus square root 5 and 2 square root 5. So we have spectral gap. K is not 0. Yeah, if K is 0, then it's 6. So this is a deep result. It follows from Ramanujan bound on fifth Fourier coefficient of holomorphic modular forms, cusp forms. And the main, so then I'm going to actually tell you, in fact, this bound is optimal. So it's by using, so I'm going to introduce a spectral measure. So let mu k be the spectral probability measure associated to this symmetric matrix, sim k of T5. So one may ask about the distribution of these points. So we know integral points are equidistributed on the ambient space. And in fact, the analog of that result is true for the dual points. So limit of mu k as k goes to infinity converges weakly to a measure which is a Plancherel measure on which has positive mass at exactly this interval. So this shows that, in fact, this is a strict bound on the eigenvalues. So it has positive mass here. So the main principle that I want to mention is that optimal spectral gap on the dual points implies sharp bound on the covering exponent. K bar is 1, and k is less than 2 for S3. So I would like to talk more about the statistics of these eigenvalues. So there are two well-known conjectures on the statistics of these eigenvalues, which are motivated by numerical experiments on these eigenvalues and also in mathematical physics. So the first one is the distribution of eigenvalues is modeled by a Poisson process. And the second one is that the multiplicity remains bounded. As k goes to infinity. As k goes to infinity. Okay. So last year I was thinking about these two problems, and one of them is basically, I found a counterexample to the first one, and I proved a partial result for the second conjecture. So I'm going to state the theorem. Sorry, 2000. This is my joint work with Jung and myself in 2018. So we proved that just an infinite sequence of weights which goes to infinity, such that the discrepancy of the measure, spectral measure that I defined there, again, natural measure, is bigger than 1 over k to the 1/3 times log k squared. So what is the discrepancy? You can think of it as you split the interval in two parts, and you count the number of eigenvalues and subtract it from the expected value. If there were randomly distributed, or it was modeled by a Poisson process, then you expect the error term to be of size k to the 1/2. But this lower bound gives us k to the 2/3. So they don't match with the distribution of random points. For an infinite sequence of weights, so we don't show it for all sequence. And in fact, I still believe for generic k, that should be true. Maybe but we disprove it for the set of all, for an infinite sequence of weights. So for the second conjecture, I look at the eigenvalues, the eigenvalue 0, which is the size of the kernel of this matrix. What is the size, the dimension of?
An analog, say, with the modular group, the mass forms where the local spacing of the eigenvalues, of course, is surprising because it's arithmetic.
That's
what would be your theorem there?
So that's something I haven't looked at, but I believe maybe it would be the case where for an infinite intervals in the weight aspect, there are some eigenvalue aspect, yes. For some infinite sequence of windows in the T, the discrepancy is high.
But it's not local spacing.
What do you mean?
I think
So you look at like a window from T to T plus 1, you still have T eigenvalues.
yeah.
And then you look at the statistic of those T eigenvalues.
The thing that's reliable is the consecutive spacing. So really
Uh-huh.
local spacing. That I'm sure is Poisson.
Uh-huh.
I mean, numerically, Schmidt
Uh-huh.
and Bogomolny found this over and over again.
Yeah, but this is also like a statistics. You can measure it against Poisson, and we are showing
What I'm saying is
this
not
doesn't
local.
match.
It's big intervals.
Uh-huh.
In other words, it's so like with the Riemann-Zeta function, you can find correlations which aren't random matrix theory if you look
Uh-huh.
at big intervals. But in the purely local statistics,
Uh-huh. They still.
so I'm not. I don't think well, we'll go.
Yeah.
Need to digest just exactly what this happened.
Uh-huh. So the proof based on Peterson trace formula and the fact that the J-Bessel function has a transition range.
Right.
So
that
this
doesn't-
kicks in the
that doesn't happen
computation.
In the mass case.
Yeah, that's something, yeah. Okay, but the result on multiplicity of eigenvalues is, the proof was deeper than this one. So I'm going to state that result. Theorem. So the dimension,
It's not the asymptotic, it's a joint. It's J at the transition probably. Right? It's a transition feature.
yeah, so
It's J, K, and
so for every actually, so this is for prime P. For every fixed prime P, there exists an infinite sequence of
I'm
weights
just saying
such
the
that.
feature of the bad distribution is coming from the transition range of the JK Bessel function.
That's right.
Okay.
Yeah.
Yeah.
So the second theorem is the dimension of the kernel of sim K of T5 remains bounded. And in fact, in this case, it's less than 21 for every K.
Yeah. If you prove that for the mass case, I'd eat my hat.
So
In South Africa.
So the proof here is based on the formation space of Galois representation, and it reduces this bound into a modularity result. So these are the known results about the statistics of the dual points.
You should mention Caligari.
Caligari's result is on. So actually, if you look at if you take any multiplicity of lambda, so here's something, yeah, it should be careful. So if lambda is a non-zero eigenvalue inside this interval, in fact, there is no bound on the multiplicity. So the multiplicity of lambda as an eigenvalue of T5 is the best known bound is by trace formula. It's K over log K. K is the trivial bounded dimension. Log K you can save by trace formula. But if you normalize the eigenvalues to be algebraic numbers, meaning that if you multiply the eigenvalues with 5 to the K half times lambda, and you ask about the multiplicity of these, then if this is the normalized eigenvalue, then the multiplicity is in fact less than the p-adic norm of this number. So the order of square. So anyway, if you look at this number, you may think that this has order k half. So square of it is k squared, which is worse than that. But in fact, for some eigenvalues, this number has finite order. And for them, this is a better upper bound. But in fact, by a conjecture of Naser and Gouveia, most of the eigenvalues here has order k to the 1/2. So this bound statistically does not tells us that much about multiplicity. What Caligari proved is that if you fix an eigenvalue with, let's say, here, in this normalization, where the eigenvalues are inside 5 to the k half 2 times square root 5, and so where the eigenvalues are normalized to be algebraic numbers, if you look at k, fix lambda and let k goes to infinity and count the multiplicity for every k, then it grows like log of k. So the result is very interesting when you go look at all the weights, not just a single weight. Then you have very few multiplicity, arbitrary log. So I'm going to go back to the integral points, and I'm going to discuss about the known results for higher dimensions. So far we discussed about S3, where we had Ramanujan. But for higher dimension, the orthogonal group does not satisfy the Ramanujan bound on the eigenvalues. So let me first mention the results for higher dimension. So by using the best known bound toward the Ramanujan conjecture for orthogonal groups, Ghosh, Grodnik, and Nouveau in 2013, they in fact proved the same bound for K3, but they also proved that let KD be the covering exponent of sum of D squares for SD, sum of D plus 1 squares. So KD bar is the average covering exponent. D is also even. So let's think about the case where 6, for example. So KD bar is 2 minus 8 over D plus 2, and KD, no, we don't have a sharp upper bound on, we don't know the exact value of KD bar yet, because we don't have Ramanujan. So these are the known bounds on KD bar and KD. So my main contribution in this subject is to show that, in fact, to give the exact value of KD and KD bar, so which I'm going to state my result maybe on this big board. This is Sardari 2015. So I'm going to state the result for every non-degenerate integral quadratic form. Let f of x1 to xd be any non-degenerate integral quadratic form in d greater than 4 variables. So let's set some notation. Let Vn be the quadric given by setting f of x to be n. If your quadratic form is indefinite, then fix omega a compact subset of V1, the quadratic at level 1. And then what are the data? Given n m lambda 1 to lambda d mod m and cap on omega. So remember, the task is we want to find an integral point on Vn such that when we project it on V1, this is omega, it lies inside a cap of size Br. So we have Br, a subset of omega. So the task we want to do is to find x inside Vn of z such that xi is coordinates. So x is a vector. I is congruent to lambda I mod m. And also, when we project x, on V1, it's lie inside the cap Br. We want to solve this system of equations. We have some in our Archimedean constraint too, so you can think of this as a cap in non-Archimedean distance. So we have some necessary condition. If we want an integral point, we better have p-adic points. So we need to assume star has solutions in ZP and R, real numbers. Then for d greater than equal than 5, star has a solution if you only need one condition, n to be greater than a constant which depends on epsilon, m to the r inverse to power 4 plus epsilon. And 4 is optimal exponent. You can't choose any power less than 4. 4 is the optimal exponent. So for d equals 4, I can show that this has a solution if n is bigger than. So now I can show that so this should be 6. So 6 plus epsilon. And again, 4 is a lower bound for the exponent. So this implies, this result implies that KD, as defined there, is equal to 2 minus 2 over d minus 1. And this recovers the Sarnak's bound on K, bigger than 4 over 3 and less than 2. But it also works for every indefinite quadratic form as well, where we don't have Ramanujan. So the proof is does not go through the Ramanujan bound. It uses a different tool. So it's based on Klosterman circle method, which is refined by Duke, Friedlander, and Ivanich, and a further refinement by Heath-Brown. So the setup that I'm using is the Heath-Brown's version of circle method, which is known as delta method. Yeah?
Even in Gorshnik and Gottlob and Levaux, the set S that you pick, you have no condition. It's not like only 5 to the power n for the sum of squares, but any integer.
I think they need to pick like p to the n. The version that I looked at was stated for integral points.
The reason is they
z 1 over p.
make S arithmetic in one place, but none of these are needed. I mean, yours doesn't require that, and nor does theirs if they do.
Uh-huh. So you think the result is also for general n, or? I think the result that I'm citing here is for p arithmetic points. You invert one prime.
When they write a number as a sum of squares, if the right-hand side is a square, then they can convert it to a rational statement, and then use.
So I'm going to state.
I'll explain to you, but this is not the secret.
So I'm going to state this is the result.
Of course, don't get the sharp thing.
Yeah. So this is the result for KD. I'm going to state my latest result for KD bar. So in fact, you can prove that for let f x1 to xd be a positive definite quadratic form in even number of d variables, which d is even. Then
You might say a word, because I don't. Usually, you think Ramanujan is going to dominate everything else in sight, because some were invented partly to give partial results towards Ramanujan. But the circle method is very powerful if you localize some variables to find regions, which is what he's doing here, and that is exactly why this method remarkably pulls out a sharp bound.
Yeah.
And by the way,
Yeah.
He actually suggested to me and then me to you that this might be true.
That's right. Yeah.
He agreed to it.
Yeah. The method, the idea that circle method works. Yes, it was.
More powerful. I didn't believe it.
Uh-huh. But for computing KF bar, in fact, using circle method is somehow hopeless because, in fact, as I said, there are some points where 4 is the optimal exponent, and if you want to prove KF bar is 1, you need a much shorter exponent than 4. So, but the proof here uses ideas in automorphic forms, and it reduces the problem again to a Ramanujan bound on holomorphic modular forms. So I'm going to state a version of this theorem, but which is slightly easier to prove. But the main ideas is already there, and I'm going to sketch the proof of this theorem. So it's elementary to state. So let A m by m be a positive definite matrix, integral matrix, symmetric matrix with determinant 1, and assume that it only represents even numbers. Which means x transpose is a vector A. X is always 2n. And what we are interested in is which numbers are representable by such a matrix. So it's a well-known result that if n is sufficiently large with respect to m, then it's representable by A.
M bigger than
Yeah, n is bigger than, I believe, m to the 1 plus delta would work.
No, M. You can't do 2 by 2 or 3 by 3.
Oh, yeah. So I'm talking about large m. Yes, m is bigger than 4, let's say. If n is bigger than n plus a power, then you can represent. So what we are interested in is in higher dimension, which numbers are representable. And the theorem that I'm going to mention is it shows a sharp transition range between the numbers which are representable and the one which are not. So let's first give a probability measure on the space of such matrices. So if we look at the finite set, so let C of A be the set of matrices which is the genus of A. It's basically the set of all matrices with this property, determinant 1, and representing even numbers, forms a finite set if I define them up to an equivalence class with A is equivalent to x transpose AX. So this is the equivalence relation. This is going to be a finite set. And there is a
X is GLN, Z.
what? X is, yes. Yeah, X is GLMZ, yes. It's a SL. Yeah,
So
GL.
all integrally, locally equivalent forms, not globally inequal.
Yes, so, and they're not, these are the classes up to this relation. So there is a Ziegel mass probability measure on the genus class, which is mu of AI is the size of the
I don't think it's mass, it's
Ziegel
Ziegel mass.
mass. Okay, Ziegel.
Mass was a Ziegel,
Yeah.
was a student of Ziegel.
No,
It
okay.
wasn't the mass.
Ziegel probability on CA. So it's
Actually, in German, I think it's weight, not mass, right? That's correct, Frank? Raphael?
Mass is
Ziegel,
just like
what
measure.
for? What?
Mass is measure.
Yeah, so weight.
So we'll take the inverse of the automorphism group of AI, the set of all matrices in GL and Z such that X, this is equal to A. The probability measure is proportional to 1 over the inverse of the automorphism group. So with respect to this probability measure on the genus, there is a sharp transition phenomena happening for this for this problem. So, which is gonna state it here. So let's give another. So I still need to define RAI of n be the number of x's such that X transpose AI X is n, the representation number of n by AI. So Siegel gave a formula. This is now Siegel mass formula, which is the expected value of this number with respect to mu is product of some local density.
Why are you interpreting my formula in such a weird,
It's
quite particular.
So in this case, one can actually compute these local densities, and it's going to be m times n to power m half minus 1 times the volume of the unit ball. So this is a very small number.
You should say what Siegel's mass formula does is the right-hand side is purely local. You just solve things in consequences and you get those numbers. The left-hand side is saying that if you sum over the genus with that weight, then the local is equal to the total. But if the genus is large, it says nothing about the individual.
So, yeah. So these are non-zero if there is no local condition, if we have points on ZP. So the main result which I'm going to state is let m naught.
And Siegel's mass formula applies, you represented scales.
Yeah. So let m naught be the point where this expected value is 1. So I'm going to denote this bar R of n. R of n is the average. So numbers. R of m naught is exactly 1. So then there is a sharp transition range. For numbers bigger than m naught, so then we have this theorem. So the probability that we represent n inside the genus class with respect to the Siegel probability equals n has this property. It's exponentially small. It's e to the pi e k minus 1 for n smaller than m naught with k units. So if you k step to the left, you are exponentially small. And if you go k step forward, plus a log term, log of m naught, then you are exponentially likely to hit to represent n. So it's 1 minus e to the.
Just coming from a comedian factor?
This one, yes.
Is it just coming from the
No, what do you mean? This one. The upper band comes from the Siegel mass formula.
No,
because
you're studying the right-hand side. And I'm saying, are you getting the answer from the right-hand side, the product of local masses?
Yeah.
Is the Archimedean mass responsible for this?
For which one? The upper one, this upper band. No, for this one, yes. I mean, I'm just computing the expected value, and the expected value is bigger than the probability. I'm bounding the expected value.
I'm asking, when you study the right-hand side of the Siegel mass formula,
Here, you mean?
you've got,
I have an explicit formula for that.
so it's just the volume that's coming. I'm just saying
It's-
that's all just coming from the Archimedean contribution.
You mean this exponential fact? It comes from here. Like if I change n to n plus 1, let's see what's going to happen. It's going to be n plus 1 to power m half, right? If I divide it by n, then it's going to be 1 plus 1 over m to power m, and then this is e to the 2 pi. Yeah. Yeah.
It's not just coming from,
No. So now let me state maybe just mention what goes in the proof. The proof of the upper one is, you can observe it here. The probability that representing a number is less than the expected value of that, because this number is 1 or bigger than 1. So in fact, if you look at this formula and what I said here, you can easily see that if you go k unit to the left of m naught, so you're multiplying with this number but to the power k. So that's a consequence of just Ziegel's formula. For the second part, I need to go through the analysis of the variance of the Z with respect to the Ziegel probability, which is a computation involved. It uses automorphic forms. But in this case, it's actually, there are some classical objects which we are working on. So I'm going to go through the proof of this result. Let me state the main formula which I'm going to use. So it's Ziegel variance formula. So it's, let's write down variance of A and N, which is exactly, you're computing the variance of, let me write N. This is exactly the sum of mu I, representation number, minus its mean squared. And it's the variance of representation number with respect to the Ziegel probability measure. This has a nice formula. It's a sum over pi. These are eigenfunction of what's called a Kessner graph. There is a graph structure on this set of points. So I told you this is a set of points, but in fact you can Kessner.
Naser or Kessner?
Kessner. No, not mine. This is
No, no. Who's Kessner? I know Knaser.
Naser, yeah. Sorry. Yeah. So, yeah, Naser give a graph structure on the genus class. So what is that? I can, it's not, maybe I just assume for every prime p, there is a graph structure on this graph. And this pi is the eigenfunction with respect to the adjacency matrix of this graph. So you get a natural weight function on these set of genus class of A.
So it's a graph for every prime.
For every prime, yes.
There are infinitely many.
There are infinitely many of them, but you just pick one of them. Which,
Oh, you just, okay.
Yeah.
So you fix your favorite prime and you go.
yeah. So now, what is the right hand?
This is some relative of this Brandt matrix, I assume, in higher quadratic.
Yeah, you look at this this as
In
a.
4 variable case, it's Brandt matrix.
So you identify it with the space of O,
Yeah, okay.
AQ, and then these are the automorphic forms which are constant at infinite place. So what is the right-hand side of this? This is the nth Fourier coefficient of the theta series associated to pi square. So what is this object? As I said, you sum this theta of pi is sum over AI, but you weight with this eigenfunction, and you sum theta of AI and Z. theta of AI and Z is just the generating function of representing numbers. So it's a theorem that it's a theorem of Siegel that these are in fact modular forms. But the interesting point is that once you average them with these weights, these are going to be Hecke modular forms.
Now, we see on that one plane because it's scalar, right?
What?
This is all scalar.
Yeah. Yeah.
I mean,
Hecke, yeah. But you can do it in every, actually. You can define the analog of these, yeah. Yeah. So these are Hecke modular forms. So you can, so the fact that they're Hecke, there is a multiplicative structure on this Fourier coefficient, which I'm going to use. So let's write down. So the proof of this theorem comes from giving a sharp upper bound on the right-hand side of this identity, which again uses the Ramanujan bound on the Fourier coefficient of modular forms. So let me just go through that. So then you have, so in fact the multiplicative structure tells you that, let's write n as 2q, as it's an even number. So this is the, let's square it. So it's going to be lambda theta pi of q times a2 of theta pi square. But by Ramanujan conjecture, by Ramanujan bound, we know that this number is less than this number square is the divisor of q square times q to the m half minus 1. So now something magic's going to happen. The variance that we started with a and 2q is going to be less than or equal than this number, q to the m half minus 1 times the sum of a2 theta pi square. So computing this like individual ones is hard, but the point is now you look at this identity again, and this is going to be the variance of a and 2. So it's going to be less than or equal than q to the m half minus 1 plus epsilon variance of a and 2. And you can do this calculation elementarily and show that this number is actually less than 10 times m squared. And use, so you plug in, right. So at the end, we're going to use a Chebyshev inequality. So then let mu bad be the probability measure that we are not representing the complement of this set. So the bad set is the complement of this set. So the measure of mu bad is less than or equal than, if I don't represent, then in the variance sum, this is 0. And the variance is bigger than mu bad times RA squared. So Rn 2q squared is less than variance of A and 2q. But on the other hand, I have a sharp upper bound, so your this is going to be R2 times this. So R2 times this exponent is going to be R2q. So you get R2q times m squared times dq. So now we cancel one R2 square R2q with the other one. Mu of bad is going to be less than m squared dq squared divided by R2Q. But as I said, this is exponential in units once you go 1 unit to the right. But these are polynomial in M. So this implies the this theorem. So I'm going to stop here.